Good day. Welcome to our presentation. Our first lesson, relations. It is when an element of one set is related to an element in another. Take for instance, this table. The table shows which of the following country have the following foods originated from. It shows the relationship of the foods to each of the countries. Seeing these ordered pairs, which would mean bibingka is related to the Philippines, kimchi is related to Korea, siomai is related to China, and so on, making them ordered pairs.
Domain is the set of all the first members of the relation, while the range is the set of all the second members. In our given relation, the first members are the foods, and the second members are the countries.
X to Y is the relation of the food to country, while Y to X is the relation of the country to food. For the relation of A to A or to itself, the domain and range will all be equal to subset of A given that A is equal to food. For example, bibingka is related to bibingka. Cartesian product. Using Cartesian product, we can specify which order pairs belong to the relation. For example, the Cartesian product for x to y or relation from x to y, we will pair all x values to y values, while for the Cartesian product for y to x or relation from y to x, we will pair all y values to all x values.
Rule number 1. Divides evenly condition. For every x value divided with y that has a remainder of 0, we satisfy rule number 1. Therefore, our obtained ordered pairs for this given relation are ordered pairs 8 and 2 and 8 and 4. Rule number 2. Less than or equal to condition. We define a relation R from A to A by the rule point X and point Y are all elements of the relation R. If X is less than or equal to Y, therefore, obtaining the ordered pairs 1, 1, 1, 3, 1, 5, 3, 3, 3, 5, and 5, 5.
Using the x is less than or equal to y rule, we will pair each element to itself and to the succeeding elements. As seen in the ordered pairs, A was paired with A, B, C, and D. The property is called reflexive because the ordered pairs A and A, B and B, C and C, and D and D, or reflexive pairs, are present in R. With the prefix IR, irreflexive property is the opposite of reflexive. Following the rule x less than y, we will not pair any element to itself, hence not producing any reflexive pairs in R. By following the rules x less than y and x greater than y, we will not pair any element to itself, just like an irreflexive property, but we will pair them vice versa, as shown, producing AB and BA, BC and CB, and the like. We can call these symmetrical ordered pairs. In anti-symmetrical property, the symmetrical ordered pairs are not members of R, and we will use the rule x is less than or equal to y. Asymmetric property is the same as anti-symmetric property. The symmetrical ordered pairs are not members of R, except we will use the x less than y rule, therefore not producing any reflexive pairs.
In this property, we'll be using the x is less than or equal to y rule and apply it on set x. We will then have R with the following sets of ordered pairs. From there, we'll be making our pairs of 4. To do so, look at the first 3 ordered pairs for reference. To produce point xy, we'll be applying the x is less than or equal to y rule to all x values. Hence the point xy or the xy ordered pairs. For yz, or point yz, we'll be applying the x is less than or equal to y rule to all y values. Finally, for xz or point xz, we will just copy the x and z values into the ordered pairs. Property, we will be applying the said rules to come up with pairs that satisfy the rules. For example, point 2, 1. Satisfying the rules because if we substitute the x and y values in the equation, we will get an answer of 3, which is greater than 0. And for the x is not equal to y, 2 is not equal to 1. For the partial order property, it satisfies if R is reflexive, antisymmetric, and transitive. It is reflexive because of the rule x is less than or equal to y. If it's satisfied, then the reflexive pairs are present in R. For example, point AA, BB, CC, and DD. It is antisymmetric because the symmetrical orders are not present in R. It is transitive because if we solve for all of the pairs of 4, all of x, z values are present in R. For the equivalence relation property, it is satisfied if R is reflexive, symmetric, and transitive. It is reflexive because reflective pairs are present in R. It is symmetric because if we look for the symmetrical equivalent of the pairs, same set of pairs will be obtained. It is transitive because as part of the transitive property, if x is equal to y, then it will be automatically be true.
Diagrams are pretty easy to make and follow. You just have to follow the arrows pointing to the numbers which correspond to the set of ordered pairs. Here are examples. Let's start with number 1. See that arrow circling number 1? That makes ordered pair 1 to 1. The arrow from number 1 to make pairs 1 and 2. The next pair, an arrow is circling number 2 to make the pair 2 to 2. And lastly, the arrow from 2 to 3 makes the ordered pair 2 and 3. At example number 2 shows the pair as has 1 and 2. So an arrow from number 1 to number 2 is formed. Next is an arrow from 1 to 3 to make the pair 1, 3. An arrow from 1 to 4 is next to make the pair 1 to 4. Next is the ordered pair 2 and 3. So an arrow from 2 to 3 is formed. An arrow from 2 to 4 is next to make the pair 2 and 4. And lastly, the arrow from 3 to 4 to make the last pair 3 and 4. Example 3 shows the pair 1 and 2. So an arrow from 1 to 2 is formed. Next is an arrow from 1 to 3 to make the pair 1 and 3. Next is 1 to 4, so an arrow from 1 to 4 is made to make the pair 1 and 4. Next pair is 2 and 1, so an arrow from 2 to 1 was formed. Lastly is pair 3 and 1, so an arrow from 3 to 1 was formed. Example 4 shows the pair 1 and 2, so an arrow from 1 to 2 is formed. Next pair is 2 and 2, so an arrow is circling number 2. Next pair is 2 and 4, so an arrow from 2 to 4 is formed. Next pair is 3 and 1, so an arrow from 3 to 1 is formed. Next pair is 3 and 5, so an arrow from 3 to 5 is formed. Next pair is 4 and 5, so an arrow from 4 to 5 is formed. Lastly, the pair is 5 and 2, so an arrow from 5 to 2 is formed. Example 5 shows the pair 1 and 2, so an arrow from 1 to 2 is formed. Next pair is 1 and 3, so an arrow from 1 to 3 is formed. Next pair is 2 and 4, so an arrow from 2 to 4 is formed. Lastly, the pair 3 and 4, so an arrow from 3 to 4 is formed. Example 6 shows the pair 1 and 2, so an arrow from 1 to 2 is formed. Next pair is 1 and 4, so an arrow from 1 to 4 is formed. Next pair is 2 and 4, so an arrow from 2 to 4 is formed. Lastly, the pair 4 and 3, so an arrow from 4 to 3 is formed. Example 7 shows the pair 1 and 2, so an arrow from 1 to 2 is formed. Next pair is 1 and 3, so an arrow from 1 to 3 is formed. Next pair is 2 and 4, so an arrow from 2 to 4 is formed. Next pair is 3 and 4, so an arrow from 3 to 4 is formed. Lastly, the pair 4 and 1, so an arrow from 4 to 1 is formed. Example 8 shows the pair 1 and 3, so an arrow from 1 to 3 is formed. Next pair is 2 and 1, so an arrow from 2 to 1 is formed. Next pair is 2 and 3, so an arrow from 2 to 3 is formed. Next pair is 3 and 4, so an arrow from 3 to 4 is formed. Lastly, the pair 4 and 2, so an arrow from 4 to 2 is formed. Example 9 shows the pair 1 and 2, so an arrow from 1 to 2 is formed. Next pair is 1 and 4, so an arrow from 1 to 4 is formed. Next pair is 2 and 3, so an arrow from 2 to 3 is formed. Next pair is 3 and 2, so an arrow from 3 to 2 is formed. The next pair is 3 and 3, so an arrow is circling 3. Lastly, the pair 4 and 4, so an arrow is circling 4.
In the first figure, we have 3, 5, and 7 for our domain, and D, E, F, and G for our range. See, as we pair each of our domain values to exactly one value only in our range. This satisfies the one-to-one condition of injective as no domain or range value repeated. For the second figure, it is not injective as D repeated because 3 and 5 are both assigned to it, therefore not satisfying the one-to-one condition. In our first figure, we have 2, 4, and 6 in our domain, and SRT in our range. For each domain value, it is paired to one value in our range, satisfying the condition that all domain and range must be used. As for our second figure, all range values are assigned to a domain value except for U, which doesn't satisfy the condition, making it not surjective. For a relation to be bijective, it should both be injective and surjective. For figure number 1, it is bijective as all domain values are assigned to exactly one value in our range, and all of our range values are used. In our figure number 2, it is not bijective because even though it satisfies the one-to-one condition, not all of our range values are used.
For all the operations we will be doing, let's use the following given functions. f of x is equal to 2x minus 1 and g of x is equal to x plus 5. For letter A, we will just substitute the value of g of x inside our f of x function. Now, we have x plus 5 inside f. Next is we use 2x minus 1 together with it. Then, we multiply 2 to the values inside the parentheses and leaving negative 1 outside. We then have 2x plus 10 minus 1, and to simplify our final answer, we have 2x plus 9. Same process is applied for letter B. We substitute the value of function f, 2x, in our function g. Continue with the operation we did for letter A, and we have 2x plus 4 as our final answer. For addition, we just simply add our functions. First, let's add the first terms. 2x plus x is equal to 3x. Then, the last terms. Negative 1 plus 5 is equal to 4. Now combine, and we now have 3x plus 4 as our final answer. For subtraction, we lay out the function values as so, and take the minus sign and distribute it among the values on our second function. We have 2x minus 1 minus x minus 5. And after completing the operation, we now have x minus 6 as our final answer. For the quotient rule, we'll just divide both functions, and keep in mind the condition where x should not be equal to negative 5, or simply put, the divisor should never be equal to 0. Hence, for this equation, x should not be equal to negative 5 as that would make the divisor equal to 0. For the quotient rule, we'll just divide both functions, and keep in mind the condition where x should not be equal to negative 5, or simply put, the divisor should never be equal to 0. Hence, for this equation, x should not be equal to negative 5 as that would make the divisor equal to 0.